One of the amazing things that a relational database knows how to do is take your queries and optimize them so that they run quickly and efficiently. And I want to talk about that process a little bit, how you can get insight into what's going on behind the scenes, and how you can optimize your queries in order to make them go fast. One of the things that you should be aware of when you're thinking about how you use a relational database is that your queries are not really procedural. We're used to doing mostly procedural programming, or what's sometimes called imperative programming, where we literally tell the computer exactly the steps we want it to go through in order to accomplish some task. In contrast to that, when you say do a SQL select statement, you're not telling the database how to go about satisfying that request and returning you the result set. You're basically just declaring, hey, I want to have this result set come back, the thing that satisfies these criteria. So what you're doing is what's called declarative programming. You're making a declaration, you're telling the computer what you want to get back, and then behind the scenes, the computer, well, the database management system in this case, is responsible for turning that declaration into a specific set of steps that it's going to execute to actually give you back those data. So that's the idea that we want to talk about here, is how does that work? What kinds of things does the database management system do? How does it come up with the specifics of what to do in order to satisfy that query? And then how can we get some information about that in order to be able to understand the performance? So the first thing to talk about here is called a query plan. This is basically the plan, the procedures, if you will, that the database management system cooks up to try to satisfy your particular request from the database. These plans are structured in kind of a tree structure, so we'll see that they have this kind of general layout. It's a nested structure, and the more complex the query, the more elaborate that tree is going to be. And each of the nodes here in this little tree is referred to as a plan node. So we have the query plan, and it consists of a bunch of nodes. And there's a variety of different types of nodes associated with query plans. One is called a scan node. This is basically the notion that you're going to have to read through a file or read over the contents of a table to find information that you're searching for. So if you have a where clause in a query, you're going to maybe scan over the contents of that table and look at all the rows and check to see if the particular fields that are mentioned in the where clause are satisfied by that particular row. And if so, then you're going to include that in the output of the query. And we'll see that there's a variety of other types of scan nodes available. There are also filter nodes to see if you need to sort of remove information from the result set as it's being created. There are join nodes that bring together multiple tables, obviously. There are nodes for aggregation, so when we're trying to do a group by operation, maybe with a sum or a count or a min or a max. And then also sorting nodes that are used when you have an order by clause. The SQL command that we use for this is called explain, and it's going to give us back information about the query plan. It's going to show us the plan as generated by what's called the optimizer. So this is part of the relational database system that knows how to take that declarative query that you give to it, a select statement, for example, and figure out the fastest way to execute it. And that's the plan that we're going to look at. One kind of comment here, that when you do these explain commands, particularly when we talk about explain, analyze later on, there's always some additional overhead that's added by the measurement process itself. That's something to keep in mind, but it isn't really a critical issue. And the output that we're going to see is going to be some confusing looking textual output, but it's organized kind of similar to the structure of the query plan itself, as we saw back here. So each of these lower level nodes in the query plan are going to represent kind of the atomic operations that you're performing at the lowest level, and then those are going to feed into higher level nodes that are going to aggregate things or sum things or join things or whatever. And what we'll see is that at the leaf nodes of this tree, we'll find kind of the basic measurement of the estimated time that those operations are going to take, and it's kind of additive. As we work our way up the tree, a given node is going to reflect its own performance costs plus those of its child nodes. And by the time we get to the top level node in the query plan output, we'll be able to see kind of the overall time and effort that's necessary in order to execute that particular query. So let's take a quick look at a very simple query here. You can see here the use of the explain command. First of all, we've got a select statement here that just selects star from an employee database. This is just a database I cooked up that has a bunch of rows in it for purposes of kind of measuring and estimating things. So that's just an ordinary select statement. And what we do to get the additional information for the query plan is we prefix that with this explain command. So we want to have the database explain to us how will it carry out this particular query, this select statement. And you can see the output here. It says, well, here's the query plan, and then it does a sec scan on employee, and then there's a bunch of numbers. So let's look at what's going on here. You can see, first of all, that there's only one node in this query plan. All we're doing basically is telling the database, let's go out to the employee table and give me back all of the rows and all of the columns in those rows. So basically what's going to happen is the database management system is going to turn that into a plan that says, hey, I'm going to give back everything in this entire table to the end user to satisfy this request. So I'm just going to work my way sequentially down the file that contains that information for that table. And that's what we mean by a sequential scan. And it tells us which table it's doing it on. It's on the employee table. Now the interesting part here is what's shown in the parentheses after that. So there's several things going on here. The first is some cost estimates. So you see cost equals 0 to 164. There's two pieces that are going on in there. The first part, the first number there is what's called the startup cost. So this is basically the amount of time that's going to be taken as part of executing this query before the relational database system can start to output stuff. Now in this particular case, it shows that that startup cost is 0. And again, if you think about what's going to happen behind the scenes, the database is going to open up the file that contains this table's information and start reading lines out of that file. It's not going to do any filtering. It's not going to do any sorting. None of that stuff. It's going to just start giving us all of the rows in that file. So it's going to immediately begin returning data to us. So that means that the startup cost is 0. If it had to do something else, like sort the rows in that table, for example, it would have to read the whole table in. It couldn't start giving us rows right away because it needs to make sure that the rows are in sorted order by some collection of columns. So there's going to be some time where it's going to have to kind of go off on its own, do that sort, and when the sort is done, then it can start returning rows back to us. In this case, however, we don't have to do anything like that, so we can just start returning rows right away. The second number, 164 in this case, is what's called the total cost. So the database is telling us that it can start returning information to us immediately. That's the startup cost is 0, and it's going to take 164 units of cost to complete this query. Now, what in the world is that unit of cost? It turns out that the most useful way to think about these numbers is as kind of a unitless value for comparison. If one query is going to take 164 units and another query is going to take 296 units and they do the same job, you want to choose the one that takes the fewer number of units. Now, the actual value that's reflected there is almost always related to the amount of time going to be taken to access the data on disk. Right, that's the slowest part of this operation. So you're aware that the processor is running at some speed, the memory is running at a slower but still very rapid speed, and then the disk drives eventually are running at a really slow speed. So the cost to fetch information off of disk that is reflected in the query is really the kind of the tall pole in the tent. That's the most expensive part. So the unit here often reflects the number of pages that need to be read from the disk. So for a longer query or query with more rows or a query that contains rows that are very wide that have lots of columns in them, you might have to read more pages off of disk or more sectors or whatever the unit is that you're familiar with or comfortable with. And that's really what's being compared here because that's what dominates the performance generally of these kinds of queries. So under the hood someplace, the database is using some information that it has about the size of the rows, the number of rows it expects to fetch back, and so forth. And it's coming up with this unitless value that's really just only useful for comparing one thing to another. One query to a different query is presumably going to use the same measurement, but we don't really know what the units are. Another thing to keep in mind about this cost figure is that it has to do with the query running all the way to completion. We've seen in the past that we can use, for example, the limit clause, which would run the query, and then it would only give us back a certain number of rows from the result set. And so although it's possible that we might sort of shut the query down early with the limit, that estimate that the query planner is giving us is assuming that the whole thing runs to completion. In other words, all of the rows in this particular case had been retrieved, whether there's a limit there or not. The next number here, you can see it says rows equals 10,000. It's a suspiciously round number, but it's there because I just inserted 10,000 random names into this employee table, and they're not even really real names. I just said like first name 1, first name 2, first name 3. But I put in 10,000 employees, so I had a significant number of rows in that table. So what this metric is telling us is the number of rows that are emitted by this node in the plan. Remember, this is just a one node plan, but we could have a plan with multiple nodes. So the number of rows that are expected to be emitted, not omitted. And again, if you think about what's going on here with this select star from employee, me telling you that there's 10,000 employees in that table suggests that, well, this plan node is going to kick out all 10,000 of those rows, and that's what's reflected here in this second metric. So it's not necessarily the number of rows that have been scanned. It might have scanned way more nodes than the ones that it emits. And for example, if we're going to have a where clause in our select statement, it would, in general, return fewer rows than there were in the original table. So the database is trying to do an estimate of the actual number of rows that it's going to return. And we'll see that it actually does a pretty reasonable job of that, even in the case where it doesn't know kind of a priori how many rows might actually match. So there's after you look at these for a while, you kind of get a sense that the database is in fact storing a bunch of additional information under the hood that helps it be smarter about making these kinds of estimates. And that suspicion would be correct. And then the final metric that shows up here in the plan node is the average width of the rows. So in this particular database table, the way that I've defined it resulted in each row occupying 21 bytes. So, or approximately 21 bytes. In this case, I think it's actually a fixed number. But if we have like varchars where the sizes of text fields can vary, the database tries to come up with an average number of bytes in each row. And again, that's going to be used to help determine the behavior and the performance of this query. If you've got a really wide result set coming back because you have a table that has many, many rows that have many values in them and long strings and that kind of stuff, the width might be really quite long. And the database is going to use that information to figure out how many times is it going to have to go to disk to fetch information in, and that's what ultimately results in the cost figures that show up in the estimate. Here's just some additional details. I've mentioned some of these already. So the cost at a particular node includes the cost of all of the child nodes. That was what I was talking about back here when I said that this node, for example, is going to have a cost maybe that it incurred itself, plus the cost of the nodes that are its children. The information that's coming back here is only information about things that the planner, the query planner, cares about. So, for example, we're not going to have any information in the query planner's output that tells us about network latency, for example. So if we're accessing a database on the other side of the planet, we've got a dodgy network connection or something like that that's going to result in low bandwidth or low speed or whatever. The query planner can't possibly know that because it's just running inside the context of the relational database management system itself. So it's really only things that are happening inside the database, none of the other attendant issues that might orbit around accessing the database, just the database itself. And then I've already said that the units are here are kind of arbitrary, but traditionally they show up as being closely related to the number of pages that need to be fetched off the surface of the disk. Okay, let's look at some really basic queries here. Go back to this same example here. We've got this explain of select star from employees. And as I've already kind of described to you, this is going to do a complete row scan, or sequential scan of the rows in that table. There's nothing that can be skipped. It can't go specifically to certain kinds of rows. We're not asking it to filter things out with a where clause or anything like that. And so we've already talked about the query plan. I want to show you one other thing here. There is a program called pgadmin. It's linked here from the slide if you're interested. It's an administration program that's written by the same people that produce PostgreSQL itself. And one of the things that it allows you to do is get kind of of a graphical visualization of these query plans, which I think can be helpful in understanding them. And so I've just kind of copied in the images that it generates here. This is their icon for a sequential scan, kind of indicating here with this arrow coming down the table that it's just going to look in all those rows. So this is a very simple one, and it obviously tells us the name of the table. And we'll see more elaborate graphical views of this as we go. Now here's an example of using that limit clause. So same query, select star from employee, but with a limit. And now what we're going to see is that there's a lot fewer rows that are going to be scanned here. This is our first example of a query plan that has multiple nodes. So every time, well, the first entry in the line is always going to represent a node, and then any place where there's another little arrow, this dash greater than thing, that's going to also indicate a node. We'll see that there's going to be other information that the query planner will output with respect to each of those nodes, but that's how you can pick out the nodes themselves. And so you can see here that the lowest level node, this sequential scan, is still there, and you'll recognize that these values are all the same as they were previously because we're basically just doing the same query under the hood and then short-circuiting that query in a way with the limit clause. So the child node here in the query plan is doing that sequential scan, and it's going to give back rows to the parent node. And that's going to be the limit node here, which is new to us, but it's got the same kind of statistics. So for example, it's telling us that its cost is 0 to 0.69. So the startup cost, like the startup cost for the sequential scan, is 0. The sequential scan is going to give back its first row immediately upon starting the query, and the limit clause, because it's going to actually give back some non-zero number of rows, right? The query optimizer is aware that the value that's being given for the limit clause is greater than 0. It's going to also give you back the first row of the query right away after 0 delay. Then the sequential scan is going to continue and could conceivably take 164 units of time here, but the database knows that it's only going to give us back 42 rows from that underlying query. So it uses the fact that it knows that there's 10,000 rows in that employee table and can do the division here to calculate how many rows it's going to have to fetch and how big those rows are and how many page reads are going to be required from disk, and it can give us a pretty good estimate of how much time it's going to take in terms of these nebulous units of page accesses. So the total time in that portion of the query plan says 0.69 units. So it's saying those first 42 rows that we're asking for are going to actually fit on one page, right? It's going to only have to go to, well, I mean, it's probably not going to read 0.69 pages, right? It's going to read one page and just give you back pieces of that. But it's less than one page that has to be retrieved from disk. It knows that the number of rows to be returned are 42, right? It's very precise in that estimation because the value is there in the limit clause. And again, the width is still 21 bytes as it was in the underlying sequential scan, because the limit clause itself doesn't do any monkeying around with the columns that are being returned by the query. And then the graphical output, unfortunately, maybe fortunately or unfortunately, it reflects kind of the process here, not so much the structure of the tree. So although in the query plan, the sequential scan is the child node of the limit node, in terms of processing the query, the employee query, the scan of employee takes place first, and we can still, it's still a sequential scan like before, and then the rows from that query are handed off to a limit operation, and that, again, a little different graphical representation. It just shows that that's going to peel off the first few rows from the result set. So again, you get a nice graphical representation of that, and it connects quite nicely with the query plan itself. Let's look at some index queries. Now, we really haven't talked about indexes too much yet, but this is a very critical performance-enhancing capability that relational databases offer. The index in this case is not too dissimilar from an index that you might find in the back of a book. You want to find all of the entries for relational algebra or something like that, you go to the back of the book and you find an alphabetized list of all the topics that are covered in the book, and you go to the R's and you look up relational algebra, and that tells you, well, that's covered on pages 102 and 107 and 113 and 156. So what you're doing by using that index is taking some sort of a search string and being able to look up immediately to find where that particular string appears in the book. The idea of an index in a relational database is quite similar. You've got some large table, and maybe it just has an unordered collection of information in it, and you want to be able to find specific rows in that table that satisfy a certain criterion. So for example, if we just have a list of employees or a list of customers, and they're not in any particular order in the original table because we've been adding them over time and we just kind of keep sticking new ones on the end of the file that contains that table, but we want to be able to find a particular customer by name very rapidly, what we do is we build an index. So the process of creating that index goes through that base table, and it finds all of the different values in the columns that we're indexing. So let's just assume, say, last name. It's going to go through all of the last names in the table, and it's going to note down which rows those last names appear in, and then it's going to process that information into an alphabetized list of last names together with the rows in which those particular names appear. Now when the database wants to do a query, say to pull up all of the customer entries where the last name is Smith, it doesn't have to scan through the entire table and just check each row to see if it matches Smith. It knows that that index contains a list of all the names, so it can go directly to the Smith entry, and since the index is built in such a way that it's alphabetized by those last names, that's a fairly quick operation. And when it gets to the Smith entry, it'll find in the index the list of rows where Smith appears in the database. In practice, it actually might be more something like the list of disk pages where there are records containing Smith, but let's just sort of ignore that nuance. So the index provides us a way to rapidly search for specific values in the underlying base table in order to improve performance. So we want to see how those indexes aid us in making the queries go faster. So we're kind of introducing the notion of indices here as we go. Here's the syntax for creating an index. An index, just like a table, is something that's created or altered or removed from the data definition part of the SQL language. So we've got create index, alter index, and drop index like you'd expect for things from the DDL. So here's an example: drop index, and then I'm dropping an index called employee first and employee last. Now, that might look weird to you because I haven't actually created those indices, but what I'm trying to indicate here in these examples is which indices are present and which are not present. So in this case, I'm basically saying I want to just get rid of any indices that might have already been there because I want to demonstrate the behavior of this query without any indexes, okay? So the query is another explain select star from employee, but now I've added a where clause. So I'm looking for the employees where the first name of the employee is less than this string first 100. And again, when I created this database, I wasn't very creative about the names of the employees in there. So it's just first-100, first-101, 102, 103, whatever the size of that table was. But that's a first name, or it's something that shows up in the employee's first name entry in the database. So first of all, we can see here that without an index, there's no additional information that the database has available to it in order to just go find all of the entries in that table where the first name is alphabetically before first-100. So we probably expect to see that it's going to pretty much just walk through this table and have to compare all of the values in the database to see if it's less than that value. So what do we see here in the query plan? Well, first of all, it shows us that it dropped the index. That's good. And then here's the query plan coming out. So sequential scan on employee. The cost, again, starts at 0 because the database can, in fact, start returning information to us immediately, potentially. And it's going to go up to 189. And it's estimating that there's 87 rows. Now this is kind of that point that I mentioned before where you start thinking, the database doesn't have an index available to it to just go immediately pick out those employees whose first name satisfies that where clause. But it's already appearing to be smarter than we think it might be in terms of how much time it thinks it's going to take. So it's coming up with some information here about how many rows it thinks it's going to have to scan and how long it's going to take to scan them. That reflects a kind of an understanding on the database's part of how many hits it's likely to find in that table for this particular where clause. So let's look at the details here. We've got a sequential scan. Remember the cost from before for a sequential scan of employees was 164. Now we see it's actually larger than that. It's showing up here as 189. Now the reason behind that is probably because the database is saying, hey, I've got to do more work here to be able to give you back the details that satisfy that particular criteria. Now, the fact that it's still thinking in terms of disk pages is a little bit mysterious, I guess, because you wouldn't think that it would take a lot more time to do those comparisons to see which rows satisfied that where clause, and it should be somewhere closer to 164. But the database clearly has some insight into this because it's saying that the number of rows that are going to be returned is estimated to be 87. So I don't know the details of this off the top of my head. You could go look in the source code for Postgres if you want to really dope it out. But my guess is that there's some information that the database is keeping, kind of metadata about this employee table, that allows it to have some statistical insights into how many rows might be reflected in this particular where clause. The width, again, is still 21 because we're giving back all of the columns. It's still select star. Now, so that's going to be the scan. And I mentioned before that in some cases here we'll see some additional information showing up in the query plan. So the very first line in the query plan and any line that has a prefix of dash greater than, right, the little arrow, those correspond to the query nodes. But in this case, we've got another piece that's going on here that just says filter, and it gives us the specifics of the filter criterion that the database is going to apply as it scans through these rows. So it's saying that the first name is less than, and then that string. And it's included some casting operations here to tell us what specific type it's going to cast those things into. But it's reassuring, I guess, to just recognize here that the sequential scan will be filtered according to that criterion, and the database therefore concludes that it's going to return about 87 rows back. Again, it's important to note here that there is no index involved in this particular query because I've explicitly taken the time to get rid of the indices if they happen to have been there from a previous run of this query. Notice that I've used this clause if exists. That's available to you in a variety of DDL statements to skip the operation if it doesn't exist. So I don't want to try to drop an index that's not there. So to avoid having to check to see if the index is present or not, you can say drop index if the index exists, and then drop this one and this one. Okay, now let's create an index and look at the impact that that's going to have on our performance. So here is the create index data definition language statement. So create index, and again, I'm using this if not exists clause, which is similar to the if exists, but because I'm creating something, I only want to try to create it if it doesn't already exist. So that just saves some monkeying around. The next argument is the name of the index. So this is similar to the idea that you can name a primary key or foreign key or whatever. So give it a name, and then you have to tell it what you want it to index. So on, and then we say the name of the table, and then in parentheses the name of the columns that we want it to index. In this particular case, I'm just saying index the first name column of the employee table. So the employee table, the base table we call it, is going to be unchanged, unmodified. It's still going to contain the data in whatever order the data was physically stored on disk. But we're going to overlay that with a new file that has this index that tells us which rows
specific values for first name appear. Again, it's probably which pages on the disk that they appear, but we'll just sort of ignore that implementation detail. So at this point, the query planner, when we do a query that involves the first name, the query planner is going to know that we have already created an index for that particular column in this table, and it's going to take advantage of that. So important to note here that this query is exactly the same as the query that I did back here, except now I have an index defined on employees' first names. All right, so let's look at the query plan. You can see first of all that there's quite a lot more going on here. So create index, that's the result of this command, and then we see the explain output. So here's the query plan, and we can see we've got some more things going on here. I've got a bitmap heap scan on employee. Let's come back to that. We'll kind of take this from the inside out. So bitmap index scan on emp first. So emp first is this index, right? That's the name we gave to the index. It's responsible for indexing first name in the employee table, but its name is emp first. So it's telling us that it's going to use this emp first index as an initial query node or an initial plan node. And what that node is going to allow it to do is go and find exactly those rows from the underlying table that satisfy this criterion. Notice that we're doing a less than comparison. So if you think about the way an index works, you've got all the A's, then all the B's, then all the C's, and so forth. What we're saying here is go to the point where we've got a value of first-100 and give me all of the ones that appear before that, because those are the ones that are alphabetically less than that value. And what it's going to be able to look up then from the index is the specific rows where all of the instances of first names less than first 100 appear. That's what this is telling us. It's going to do a scan on that index. You can see here the cost values are also kind of sensible here. We've got, first of all, the least cost is 0. Well, why would that be? Well, we're asking for a less than query, and we know that we have an index that has the values for first name in order from the lexicographically first value up through the last. So because we're asking for things that are less than first 100, right? We know that the everything up to that point in this indexed list of rows is going to be returned. So we can immediately go to that very first entry in the base table based on the contents of the index and start fetching rows out. So we can immediately start returning things, which is why the startup cost is 0 for this query node. And then the overall cost is only 4.94. So again, the database is got some information that knows about how many rows are going to be present for this particular where clause based on its understanding of the structure of the underlying index. So this is obviously quite a lot less elaborate than, in terms of the cost, than doing a complete sequential scan. It's only going to scan those first rows, basically 5 pages, and it's going to tell us that it's going to return 87 rows in those 5 pages. Now the width is a little weird here, right? We're not talking about the pages of the underlying base table. There's the base table that has the employees in it, and then there's the index, which is a separate structure, a separate file that's ordered differently and that the database can use to go find the values in the base table. So in this case, the width is just set to be 0 because all we're talking about at this point is reading stuff out of the underlying base table. It also reminds us here that the index condition is that same comparison statement. So that second node, the child node of the query plan, is going to give us back a list of those rows where the database is going to find employee records that satisfy that criterion. And that's then going to be made available to this second node, this bitmap heap scan. Now we're going to see that it's going to scan the employee table. And the cost information is important here. We can see, for example, first that the startup cost is 4.96. It's just a wee bit larger than the 4.94, which is supposed to be the total cost for scanning the index.
remember that we had to look through the index to bring back those rows that will contain employees that have those employees that satisfy that criterion. So that's got to be completed first before the bitmap scan of the employee table itself can start giving back rows. And that's why this startup cost is just a little bit larger than the total cost of the underlying index scan. And then the total cost for the top level node in the query plan is 73.4. Right, so quite a lot less than 180 whatever it was on the previous example, because we're now going to just go directly to those locations in the underlying employee table and fish out the specific rows that satisfy that criterion. There's 87 rows estimated to come back, which matches the information that came out of the index, and the width of those rows is now still 21, which is the size of the underlying table. Again, here's a two-step plan, right? The child node, the bitmap index scan, is going to look in the index to find the rows that match that condition. And then the plan in the upper node is to just fetch those rows. Now, why is the number here in the total cost so high? Well, my assumption is that there's going to have to be multiple pages from disk that are retrieved by the database that are going to maybe each require a specific scan to get to those pages. So the fact that we're only retrieving 87 rows, which might fit on fewer than 73 pages, is not the case here, because we're going to have to skip through the entire table potentially to find those rows that were specified by the index. And the Database Management Systems Query Planner is estimating that that's going to take 73 units. So it's still going to be a win compared to a sequential scan with no index, but it's not free either. That's what I'm kind of getting after here. Fetching separate rows is going to be more costly than reading sequentially. That's why it's going to cost a little bit. So not all of the pages have to be read. So it's still going to be cheaper than a sequential scan. We don't have to look at every single page that contains the employee data. And the upper plan is going to sort those row locations into their physical order. We've got to be able to go get the actual data physically off the disk in whatever order it appears. And this bitmap idea, we're not going to drill into a whole lot, but basically the bitmap index and bitmap heap is a way to use a bitmap to come up with information about what is going to be the optimal order in which it's going to access physical pages. And finally, you can see the little icons that the PG admin program uses to give you an indication of how this works. So the emp first is the index that we're using. You can see that it's got the little table with a kind of an outboard structure that is the index that tells you which rows of the underlying table have the information of interest. And then the details from that is fed into the next portion of the query plan, where we're going to look at the employee table by grabbing the specific indexed values out of that table as indicated. Okay, so let's come up with a little bit more elaborate query. Back here we were saying the query was where first name less than first 100. So I've got that same conjunct here, first name less than first 100, but I'm going to add a second conjunct, and last name is greater than last 100. And then before I do that explain, I'm going to monkey with the indices here a little bit. I'm going to make sure that I do not have an index for employee last name. And I'm going to create an index, if it doesn't already exist, which it does right now, for employee first name. So I just want to guarantee that I've got an index that's going to be useful for this portion of the where clause and not for this portion. So here's the plan. It comes back and says basically that we have, again, starting from kind of the inside out, first of all, we're going to do pretty much exactly what we did in the previous example, right? I've got a bitmap index scan. It's got a cost of 0 to 4.94, bringing back 87 rows that correspond to those rows in the table where the first name is less than this first 100 string. Now, we're going to hand those rows off to the upper level in the query plan, which is going to do, again, a bitmap heap scan on employee. And it's got fairly similar cost estimates, slightly smaller number of rows than we had before. Notice down here we're saying still 87 rows, but up here it says 80, and then the rows are the same width that we expect. So what's different? Well, it's the fact that we've got this additional conjunct here. Now you notice that the database doesn't have any additional information because I got rid of this last name index, if it happened to have been there. The database doesn't have any additional information that it can use to go sort of directly to those rows that have a first name that satisfies the first conjunct and a last name that satisfies the second. So basically what it's got to do is get the rows that satisfy this criterion, which it can derive from that first name index that's present, but then it's just going to have to look at all those rows and check to see if the last name is greater than last 150. And that's why we get a different number of rows from this portion of the query, and you'll see here there's an additional filter going in that is going to apply to see if the last name is greater than last 150. So again, these additional lines here below the bitmap heap scan node just give us some additional information about what's going on in more detail. So in this particular case, we're looking at all the rows that are being processed by that scan and verifying that the last name is greater than that value. And if it is, that's kept into the result set, and it becomes one of these 80 estimated rows that are going to be generated. And if it doesn't satisfy that comparison, then it's dropped from the result set. So we added this condition on last name, but it's not indexed, and that's why we're just doing a filter node instead of something more elaborate that would let us go directly to those rows. So it reduces the row count that's coming out at the end, and it doesn't really affect the cost because we still have to scan all of those rows based on the location of the rows that had the appropriate first name. And once that's read into memory and we've paid the cost of that access, we can then throw some of those away if the last name criteria doesn't work. But again, the cost estimates are due to disk I/O, which is the most important element of this, and we still had to go fetch those same rows that satisfied the first name criterion based on the index. Let's look at a query that's going to get us a row by primary key. I haven't shown you the DDL for this little employee table, but you can imagine what it looks like. It's fairly simple. An employee ID is defined to be the primary key. It's an auto-incrementing serial type column. Now, we haven't ever really talked about how a database implements a primary key. We know that it's supposed to be unique. We know that it's used to look up information in that table by primary key. It's normally used for relationships between tables where a foreign key someplace else is going to point to the primary key in a table. But what is the actual implementation under the hood? Well, it turns out that it's just going to use an index. So the first thing that gives us is a quick way to look up rows in a table by their primary key, because the index is on that primary key. So we could search that index file itself to find the specific location where that particular row lives in the underlying base table. Now, there's one other nuance here that's something we haven't talked about so far. When we've seen the indices that we created on that employee table, for example, the first name index, it's certainly possible that we have employees that have the same first names, right? So that type of index doesn't necessarily require unique values. I don't want to only allow us to be able to hire one person named John and one person named Sue. So they aren't primary keys, but they're still indexed. So just like in a book index, you might have multiple occurrences of the same word that's in the index, and you're going to have all of the page numbers where that word appears. We can also define an index that does guarantee uniqueness. So instead of just saying, I want to find out a way of storing the order of the values in this particular column and then let you know where the rows are that contain those values, you can also specify that the index needs to be unique, which is going to bring into the picture the same kind of behavior that we have on primary keys. So for example, in an e-commerce database, I might define an index on an email address for my customers, because I might want to be able to look up their information by their email. When they log in, maybe the email address is used as their user account identifier. So in that case, I want the index so it's fast, but it also seems like a reasonable business rule for us to say, well, no two people should be allowed to have the same email address, particularly if I'm using it as an account name. I want to guarantee that that's never going to happen. So I can define an index for performance, but I can also say that I want that index to be unique. And then if I try to insert a row that has a
an email address that already exists in the database is going to prevent that from happening. So it's going to guarantee improved referential integrity for me. That's the type of index that's used for primary keys. So when you define a primary key, under the hood, the database is going to create an index that has all of the columns for the primary key. In this case, there's just one, but we can have composite primary keys, as we know. And those are also going to be declared to be unique, so that if I try to insert a second row that has the same values for the primary key field or fields, the database will prevent that from happening. So here we're using that unique identifier, that primary key, which is indicated in the database by using a unique index on this employee ID field. So we can see here that we're doing a scan using employee P key, right? That was the primary key name that was created when I made this table. It's on the employee table. We can see for reassuringly, I guess, that the number of rows the database thinks we're going to fetch back is 1, which, it should be because this is a primary key. And that because we're asking for all of the columns in the result set, we're going to have that same width that we've been seeing. But the cost here is a little unusual. It's not 0, which is something we haven't seen a lot of, and it's got this sort of weird upper bound of 8.3. So why is the startup cost not 0, and why do we have this weird upper bound? Well, remember that the index itself is going to be stored in a file someplace. And because we don't want to load that entire file into memory, it might be, hundreds of millions of rows in a big system, we want to actually go out to disk and find the particular value that we're searching for, the 372 in this case. And we might have to go to multiple pages on disk to sort of find our way through that very large collection of employee ID values until we can locate the page on which 372 exists in the index. So we're going to have to do some disk access. We might get lucky and find it on our first page, but we might not. We might have to sort of do what amounts to a search across multiple nodes in a tree of disk pages that contain this information to go to as many as 8-point-some pages. So somewhere in there, we're going to find the specific location of that employee record that has that key. Or if the key doesn't exist, we don't have an employee with that primary key, then we also want to know that. And then the final stage here would be to go to the actual employee record, which apparently the query optimizer kind of wraps into the cost estimate here, that it doesn't have to do any kind of scanning. It's only going to go to one place in the underlying employee table, which it just includes in the estimate.